Hello everyone, my name is Vinayak Rahatankar and today I'll be presenting on logistic regression, intuition and use cases. Logistic regression might sound a little technical at first, but it's actually one of the most intuitive algorithms in machine learning. What makes it special is that it helps us solve everyday yes or no decisions in a very systematic way. Let's start with a simple question. Why do we even need logistic regression? In our daily life, we often face binary choices decisions that have only two outcomes. For example, should I carry an umbrella today if the sky looks cloudy? Should a bank approve or reject a loan? Should an email be marked as spam or kept safe in the inbox? Machines also face the same kind of decisions. Logistic regression is the tool that helps them make these yes or no choices clearly and reliably. It is valuable for a few reasons. First, it is simple and easy to understand. You can clearly see why the model made a decision. Second, it works really well for binary classification problems like true or false, yes or no, 0 or 1. Third, it doesn't just give a fixed answer. It also provides a probability. For example, instead of just saying yes, it will rain, it can say there is 75% chance of rain. Finally, it is fast and efficient. That makes it a great starting point in many situations. Now that we know why it's important, let's move on and understand what logistic regression actually is. Logistic regression is a supervised machine learning algorithm. This means it learns from past examples where the outcome is already known. It is mainly used for binary classification situations where there are only two possible outcomes. The key difference from linear regression is this. Linear regression predicts continuous values like a house price or exam marks. Logistic regression, on the other hand, predicts probabilities between 0 and 1. For example, suppose we want to predict whether a student will pass an exam. Linear regression might say expected marks xt2. Logistic regression instead says there is a 78% chance the student will pass. This probability is then compared with a threshold, usually 0.5. If it's above 0.5, we say the student will pass. If it's below 0.5, we say the student will fail. So, logistic regression is basically a combination of linear modeling and probability estimation, which makes it excellent for clear yes or no decisions. Now, the real magic behind logistic regression comes from something called the sigmoid function. Let's look at that. Without the sigmoid function, logistic regression would just be linear regression. The sigmoid function is what transforms raw scores into probabilities that we can actually interpret. Here's how it works. If the input score is very positive, the sigmoid pushes it close to 1. If the score is very negative, it pushes it close to 0. And if the score is exactly 0, the sigmoid maps it to 0.5. When you plot it, the graph forms a smooth-shaped curve. On the left, the curve stays near 0. On the right, it approaches 1. In the middle, it rises steeply through 0.5. In logistic regression, this is how we decide if the probability is greater than or equal to 0. 5. We predict class 1 or yes. If it is less than 0.5, we predict class 0 or no. To really understand how this works, let's walk through a practical example. Imagine we want to predict whether a customer will buy a car. We start with the input features. Suppose the customer is 30 years old and earns 50 per month. These details are fed into the model. The model first calculates a raw score. In this case, the score is 0.5. On its own, this number doesn't mean anything. But when we pass it through the sigmoid function, it becomes a probability of 0.38 or 38%. That means the model believes there is only a 38% chance this person will buy a car. Since 38% is less than 50%, the final prediction is no, the customer will not buy the car. Now let's change the situation. Suppose the same person has a higher salary of 70, 0. The model recalculates, and this time the probability is 0.75 or 75%. Since this is above 50%, the model predicts yes, the customer will buy the car. The key takeaway is that Logistic regression doesn't just give a yes or no answer. It also provides a probability, which shows how confident the model is. In this case, 38% shows low confidence in buying, while 75% shows high confidence. This is the beauty of logistic regression. It takes raw numbers, converts them into probabilities, and then makes decisions that are simple, interpretable. Now let's look at where logistic regression is used. In healthcare, it predicts the chance of a disease, like heart problems, using age, blood pressure, or lifestyle. In finance, banks use it for loan approvals by checking income, credit score, and past history. In marketing, it helps find customers who may leave, so companies can offer better plans to retain them. In e-commerce, it classifies product reviews as positive or negative, improving recommendations. In human resources, it predicts which employees may leave, helping companies improve retention. So, across many fields, logistic regression supports smarter and faster decisions. Logistic regression is very useful, but it's not perfect. It assumes a straight line relationship between inputs and the outcome, which isn't always the case in real life. It also struggles with complex, non-linear patterns and works best when we have enough data. With very little data, the results can be unreliable. Another issue is outliers. Just one unusual data point can throw off the predictions. It's also limited to yes or no type problems, or a few categories. It can't predict continuous values like stock prices. And if features are too similar, like height in inches and height in centimeters, the model can get confused. So, while logistic regression is simple and powerful, it's not the best choice for very large or highly complex problems. So, let's wrap up what we studied today. We learned that logistic regression is a supervised machine learning algorithm mainly used for classification tasks. Its power comes from the sigmoid function, which converts raw values into probabilities that are easy to interpret and use for decision making. We saw how this approach is applied in many real world areas, from predicting diseases in healthcare to approving loans in finance, to detecting spam emails or predicting customer churn in marketing. At the same time, we also acknowledged its limitations. Logistic regression works best for simple binary or multinomial problems, but it struggles with very complex or highly nonlinear data. Despite these challenges, logistic regression remains one of the most important and widely used algorithms. It is simple, efficient, interpretable, and serves as a foundation for understanding more advanced machine learning models. Thank you.